Good afternoon, everyone. My name is Anatoly Gorbenko. I am from Leeds Beckett University School of Computing. And on behalf of my colleagues from the Newcastle University and the Odessa Technological University, I'm going to present our experience report entitled Interplaying Cassandra NoSQL Consistency and Performance, a Benchmarking Approach. My talk will be organized as following. In the beginning, I will give you a brief introduction into the NoSQL, Cassandra, Internet Scale Replication, and the CAP and the PASSEL theorems, capturing the major interconnection between consistency, availability, latency, and partition tolerance of distributed replicated systems. Then, I will describe our experimental methodology and setup, and will present and discuss with you the benchmarking results, quantitatively evaluating interdependency between performance and consistency of such systems. And finally, I will discuss an experimental-based methodology that we put forward for optimizing consistency settings at runtime. Well, the major aim of our work is quantitative evaluation of the fundamental trade-offs between the data consistency and performance of the Cassandra NoSQL, which itself is a common example of a new type of data storages used nowadays to handle big data. As a result of our work, we also would like to propose a benchmarking approach to enhancing Cassandra performance under mixed workloads by optimizing consistency settings dynamically at runtime. NoSQL, which stands for Not SQL or Not Only SQL, is a new generation of the Internet scale data storages which have been introduced to deal with the big data issues. First of all, volume, velocity, and variety of data. Cassandra NoSQL is one of the top 3 in use NoSQL databases today, which supports tunable consistency. So top 3, I mean Cassandra, MongoDB, and HBase. Originally, it was developed by Facebook to power the Facebook inbox searching feature. And Cassandra offers the distribution design of Amazon DynamoDB with the data model of Google Bigtable. And what's important is support tunable consistency. So you can change consistency settings and see how the consistency affects system latency, for instance, or system performance. Well, Internet scale replication and scalability are in the very nature of NoSQL databases. It enables high performance and low latency, high availability and fault tolerance, and also a disaster tolerance because we don't put all eggs into the same basket. At the same time, the crucial decision is how we update these distributed replicas. Synchronous updates cause latency issue because updates need to be propagated to all replicas before committing a transaction. With asynchronous updates, queries are executed much faster. However, some user can read stale data, which causes a consistency issue. And obviously, there is a partitioning issue. The more replica we have, the higher chance the partition happens. And because they are distributed across the internet, you know that the internet is not really the very reliable media. It's prone to congestions, message loss, failures, and so on. Well, the CAP conjecture, which first appeared in 1999 and was proposed by Brewer, defines a trade-off between system availability, consistency, and partition tolerance. It states that the only 2 of the 3 properties can be preserved in distributed replicated system at the same time. The PASSEL theorem is a further refinement of the CAP. It suggests that in case of a partition, the system trade-offs availability and consistency, else the system trade-offs latency and consistency. Though CAP and PASSEL theorems helps developers to understand the fundamental trade-offs between the key properties of the distributed systems, these theorems consider this property as binary. However, our vision is that the CAP and PASSEL properties needs to be viewed as more continuous than binary. Indeed, the availability is measured as usual between 0 and 100%. Latency, which is a response time, can be theoretically vary from or between 0 and the infinity, but in practice it is limited by the timeout from the write. Consistency is also continuum, ranging from weak consistency at one extreme to strong consistency on the other, with varying points of eventual consistency in between. And the architect of modern large-scale systems such as Facebook, Twitter, and many others, they often decide to relax consistency by introducing asynchronous data updates in order to achieve high system availability and allow quick responses. However, we believe that the most promising approach is to try to balance these properties rather than give up one of them. Cassandra is quite unique NoSQL database because it supports tunable consistency model ranging, so it ranges consistency levels from the weak to strong consistency. It provides a discrete set of consistency levels specifying a number of replicas querying in each read and write operations. For example, the consistency level 1 means that the data must be written to at least one replica node before acknowledging the write operation to a client. When reading data, Cassandra queries and return a response from a single, usually the nearest replica, with the least network latency. And the sum of nodes written and read being greater than the replication factor always ensures strong data consistency when a read never misses a preceding write. So this means, for instance, if the replication factor is 3, so if we read to one node and read from one node and write to 3 nodes, this guarantees a strong consistency. If we read from 2 nodes and write to 2 nodes, it's also guarantees a strong consistency. And finally, if we read from 3 nodes but write to 1 node, it also guarantees a strong consistency, because in all these cases, like number of nodes written and read are higher than 3. So if we consider this example. Well, as I said earlier, our aim was to evaluate quantitatively, not just qualitatively, how consistency settings under different workloads affect the read-write latency and throughput of Cassandra NoSQL. The 3-replicated test-bed system was developed and deployed on Amazon clouds. We used a popular Yahoo Cloud System benchmark, which is a default standard to benchmark cloud systems and NoSQL databases. So we use this benchmark to run our experiments, and we range the workload from 10 to 1000 threads. Here you could see all the rest consistency settings. So we benchmark our system for under different consistency settings, one all quorum for different operations, reads and writes, and well, so number of requests in each thread was 100. Well, so we have collected a few hundred megabytes of raw data, so quite a lot. And here you could see an example of how it looks like, so how the data looks like. So we measured latency for each and every read and write operations for 3 different consistency settings, one, quorum, and all. And here you could see that on the graph, you could see that the X is a request number, and Y is a latency, is a time, so it's a response time for each of that request. So what we observed is that there is a cold start phenomenon, which was further excluded from the analysis, and there is also a few straightforward like findings. The first one is that writes are faster than reads, which is in the very nature of Cassandra, because it was designed to support really fast writes. We can notice that all consistency level causes the slowest read-write operation, one consistency level causes the fastest read-write operation, and the quorum provides a nice compromise between one and all. From the raw data, we evaluated the average system latency and throughput. So here you can see that the system is saturated with around, the system's throughput is saturated with around 800 threads. Delays become highly volatile when Cassandra operates close to the maximum throughput, so it's also clearly shown here. Writes executes under the one consistency level reach the maximum throughput of more than 13,500 requests per second. The quorum and all consistency throughput fluctuates around 13,000 and 12,500 requests per second. And the maximum throughput of read operation is lower than the throughput of writes by 21, 33, and 38% correspondingly, depending on the consistency settings. When Cassandra is configured to provide consistency level 1, the latency of both read and write operation is lower than the average response time of all consistency settings by 13 and 26% respectively. So this is now we're talking about the latency, not the throughput. The quorum setting demonstrates a rational balance between delays and data consistency, and as expected. And besides, our results confirm the claim that Cassandra has very high write speed, especially under the heavy workload. And indeed, you could see that the writes are almost 25% faster than average than reads operation independently on the consistency settings. Benchmarking results reported earlier actually they are discrete set of measured values. So they don't allow system developers to precisely estimate the database latency throughout the whole range of possible workloads. Thus, a regression functions estimated from the experimental data using, for instance, the least squares can effectively solve this problem. And here you can see the latency regression that we estimated for our data, for our statistics. And the goodness of it, the tests show that the polynomial regression of the fifth order fits our experimental statistics with the highest accuracy. Obviously, regression functions presented here are unique for our experimental setup and will not exactly match other installations. Thus, this simply means that the system developers they will need to find the equation which will theoretically fit their own benchmarking result. And there is a variety of tools and APIs which can do this. So this is not really a problem. Well, as I said before, the Cassandra can guarantee the strong data consistency if a sum of replicas written and read is higher than the replication factor. Besides our experiments, so it means that in total we have 6 possible combinations. However, our experiments clearly show that the fewer replicas are invoked, the faster Cassandra performs read and write operation. And actually there is no surprise for this. Thus, if one would like to ensure that the read operation always reflects the most recent updates, so if one decides to provide the strong consistency, he or she needs to choose between the 3 following settings: 1 read, 3 writes, 2 read, 2 writes, or quorum read, quorum writes, and 3 read, 1 write. I'll call them 1R, 3W, for instance. Hence, we can predict the average Cassandra latency under the mixed read-write workload with the following equation, which are presented here, making use regression function reported on the previous slide. The Cassandra database is known for extremely fast read and write updates. Thus, one might decide to opt for 1 read, 3 write settings to guarantee the strong consistency in all possible workloads. However, our estimates show that the 1R3W settings doesn't really provide the lowest response time in all possible scenarios. The 3D service plot on the slide demonstrates that there are domains in the input workloads where a particular consistency settings provides the best performance. And here you can see that there is a domain for 1 writes, 3 write, 1 reads, 3 writes, 3 read, 1 writes, and even quorum. So depending on the workload and a ratio of reads and writes operations, opting for quorum or for 2 reads, 1 writes will improve the Cassandra performance up to 20% in our example. Obviously, it's about in our example. In other example, it can be different, but there is no doubt that there are specific domains which is better, where it's better to choose this or that consistency settings. One might note that the data reported and the regression function used are unique for our experimental setup and might not exactly match other installation. And this is generally true. And obviously, Cassandra latency depends on many factors, including the database structure, used hardware, the number of nodes, their number of replicas, the distribution of nodes, workloads, and so on. So we propose a methodology to be used by system engineers for predicting the Cassandra latency. And what's important for choosing the optimal consistency settings at runtime, depending on the workload and the read-write ratio. So during the system settings, we propose to benchmark Cassandra performance and the different workloads and different consistency levels. Then, based on the collected statistics, the regression function of the average read-write latency needs to be identified. This could suggest the optimal consistency settings for different workload domains and read-write proportions. So we can find the domains for the certain system, for the particular system. And the last step should be performed at runtime during system operation. So the optimal consistency settings can be selected, can be chosen by monitoring of the current workload and the read-write ratio, making use of the domain that we identified during the system load testing. So we have verified our methodology by running a series of benchmarks, and here you could see the table which presents the deviation between the experimental data and the theoretical data, and the average deviation is about 2%, so it's really low. And in the worst case, it was 60%, and but what's important that the number, this number is reducing with the workload increase. And finally, what's also important that our methodology suggests the optimal consistency settings in 92%. So it's really accurate, and then it shows that yes, using the approach that we propose, we can provide and we can improve the performance of the systems. Well, up to 20%. 20%, one might say that it's not really a large number. What is from the other hand, 20% is 20%. Well, and we can draw some conclusions. First of all, as I said, our work experimentally investigates the interplay between different consistency settings and the performance of the Cassandra NoSQL database. And we believe that the consistency, availability, and latency must be considered as continuous, not binary, in contrast to non-CAP and PASOX theorems. And it is clear that the strong data consistency settings worsen the database latency. However, numbers are important, and in our case, it worsened by 25% for reads and 13% for writes. So you can evaluate the consequence of choosing this or that consistency settings. And it is also clear that the strong data consistency, it is also clear that the optimal consistency settings depend on the current workload and the ratio of read and write operations. And what's important that it is impossible to make the best offline decision. Thus, we have proposed a methodology to optimally balance consistency and performance dynamically at runtime. This is all, so thank you very much for your attention.